The wrong choice is the right one. You've been taught your entire life to find the winning strategy and to stick to it. Think about it. You find the best route to work, the best restaurant in town, the best framework for your project. And once you find it, you exploit it. You use it over and over because, well, why would you ever choose the second best option on purpose? It seems logical. It seems smart. And it is completely, fundamentally, wrong. Most people think the goal of intelligence is to always pick the winner. They're wrong. And frankly, they're leaving value on the table. They get stuck in this loop of good enough, without ever discovering what's great. This is the central problem of reinforcement learning. It's not about being right 100% of the time. It's about knowing when to be wrong. In this video, I'm going to show you why being stupid 10% of the time is the single smartest thing you can do. We're going to break down the classic multi-armed bandit problem, and I'll introduce you to the one simple counterintuitive algorithm that solves it: Epsilon-Greedy. And this isn't just some brain teaser. This is the bedrock. Understand this one idea, this balance between exploring new options and exploiting the ones you know work, and you unlock the core logic behind every single reinforcement learning agent. I'm talking about everything from the agent that beat the world champion at Go to the one that's probably trying to sell you something on Amazon right now. So, to understand how AIs really learn, we're not going to start with code. We're going to start in a casino. Which brings us to our next section, the casino dilemma, your high-stakes test. All right, forget the theory for a second. Let's make this real. Imagine you walk into a casino, and right in front of you, just like you see here, is a row of 10 slot machines. You have 1,000 tokens in your pocket, not one more. Your goal is simple: walk out of this casino with the most money possible. But here's the catch. Each of these 10 machines is programmed differently. One of them might be a secret jackpot machine, paying out huge rewards on average. Another might be a total dud, designed to just eat your tokens. And the rest are somewhere in between. The problem? You don't know which is which. Their true payout rates are completely hidden from you. So, how do you play? What is your strategy for spending those 1,000 tokens to maximize your winnings? Do you pick one machine and stick with it? Do you try each one a few times? Do you have a system? This isn't just a brain teaser. This little casino game is the perfect, simplified model for the most important trade-off in all of reinforcement learning. In our world, we don't call this a row of slot machines. We call it the K-armed bandit problem, where K is just the number of machines or arms you can pull. And let's put some official nerdy labels on this so we can talk about it like pros. Don't worry, this is just giving names to things you already understand. Look at this. An action A is just your choice of which machine to play. The reward you get back, RT, is the handful of coins the machine spits out at that time. And here's the important one. Each machine has a true hidden average payout. We call this its action value, which we write as Q*A. This Q*A is the number you wish you knew. It's the true jackpot potential of each machine. Now, formally, it looks like this. Check out this formula on the screen. I know, your eyes might glaze over when you see that. Don't let them. That's what they want you to do. They want you to think this is complicated. It's not. All this formula says is, the true value of an action A is just the expected or average reward you'll get, given you chose that action. In casino terms, it's the machine's true average payout over the long run. Simple as that. The entire game, the entire challenge, boils down to one single fact. You don't know Q*A. You have to figure it out by spending your precious tokens. And this creates the core conflict. With every single token you put in a machine, you face a dilemma. A choice between two opposing ideas. First, there's exploitation. You've tried a few machines, and machine number 7 has paid out pretty well so far. Exploitation means you stick with what works. You pull the lever on machine number 7 again, because based on your limited experience, it's your best bet to make money right now. You are exploiting your current knowledge. But then, there's exploration. You look at machine number 4, which you've never even tried. Or you go back to machine number 2, which gave you nothing the first time. Why would you do that? Because your knowledge is incomplete. Machine number 7 might not be the real jackpot. It might have just gotten lucky. By trying another machine, you are exploring to improve your knowledge of the world. And here's the kicker. You cannot explore and exploit with the same token. Every time you choose to explore a potentially worse machine, you are giving up a goodish payout from your current favorite. But, if you only ever exploit your favorite, you might be stuck on a decent machine for all 1,000 turns, never realizing the true jackpot machine was sitting right next to it the whole time. This, my friends, is the exploration-exploitation dilemma. It is the foundational trade-off of all reinforcement learning. Get this balance right, and you can build systems that learn and adapt in the real world. Get it wrong, and you build agents that are stubborn, stupid, and get stuck on the first good enough idea they find. So, how would you play? What's the most common sense way to solve this? In the next section, we're going to look at the obvious strategy and watch it fall right into a trap. Okay, so you're standing in front of the 10 slot machines. You've got your 1,000 tokens. You understand the dilemma. So what do? What's the most common sense, logical, smart person strategy? Well, most people would say something like this. First, you'd try each machine a few times, just to get a feel for them. Second, you'd keep a running average of how much each machine has paid out. And third, from then on, you would always pull the lever of the machine with the highest average so far. This is called the greedy strategy. And it sounds right, doesn't it? I mean, you're using data. You're making an informed decision at every single step to maximize your profit. You're being efficient. Let's put a tiny bit of math on it just to be precise. First, you need to estimate the true value of each machine, since you can't see it directly. We'll call your estimate QTA. The Q stands for quality, and the easiest way to do this is with a simple average. Check out the formula on screen. All this is saying is that your estimate for a machine is the total rewards you've gotten from it, divided by the number of times you've pulled its lever. Easy enough. If you pulled a lever 3 times and got back 2, 8, and 5 coins, your estimated Q value is 15 divided by 3, which is 5. Second, you apply the greedy rule. You always choose the action that currently has the highest estimated value. We write this with a fancy function called argmax, which you can see here. Don't let it scare you. It just means give me the argument, the thing, that produces the maximum value. In our case, it just means pick the machine with the highest Q value. This is the system. This is the logical approach. And it has a fatal, catastrophic flaw. The greedy strategy is too quick to judge, and it never looks back. It gets trapped by its own early experiences. Let's watch it fail. A simple, brutal example. Okay, let's imagine a smaller casino with just 3 machines. And here are their hidden, true average payouts. Machine 1 is a dud. It pays out 2 on average. Machine 2 is pretty good. It pays out 8. And Machine 3 is the real jackpot, paying out an average of 15. Now to get started, our agent decides to try each machine just once. The game begins. First pull. The agent tries machine 1. The reward is 2. So in our agent's brain, its estimate for machine 1, Q of 1, is now 2. Second pull. The agent tries machine 2. It gets a slightly lucky pull, and the reward is 10. Now its brain says, okay, Q of 2 is 10. Third pull. The agent tries machine 3, the actual jackpot. But, by pure bad luck, this one single pull gives a disappointing reward of only 7. The agent's brain now says, Q of 3 is 7. The trap is sprung. After just 3 pulls, look at the world from the agent's point of view. Check out this table. Its beliefs, its Q values, are 2 for machine 1, 10 for machine 2, and 7 for machine 3. So now the greedy strategy takes over. For pull number 4, and for every single pull after that for the rest of its life, which machine will it choose? It will always check its Q values. It will always find that 10 is the maximum. It will always choose machine 2. Forever. It will never ever go back to machine 3. Why? Because based on its one single unlucky experience, it believes that machine 2 is the best. It's locked in. It's become stubborn. It got stuck exploiting a pretty good option, and it will never discover the true jackpot sitting right next to it. It's trapped in a loop of good enough. This is the failure of pure exploitation. The agent's initial bad luck created a flawed worldview, and its greedy strategy gives it no way to question that view. It's going to spend its remaining 997 tokens on the second best machine, leaving a mountain of cash on the table. So how do we break this? How do we build an agent that isn't so stubborn? How do we force it to look again, to challenge its own beliefs, even when it thinks it knows the answer. That brings us to our first real powerful solution. A fix that is so simple it almost feels like cheating. It's called the 10% fix, the Epsilon-Greedy method, and it's the subject of our next section. So, our greedy agent is trapped. It's stuck pulling the lever for machine number 2 for the rest of its life, convinced it's the jackpot, while the real treasure is sitting right next to it, completely ignored. The logical, common-sense strategy failed. So how do we fix it? How do we break it out of this trap? You might think the solution has to be some complicated PhD-level math, another spiderweb diagram of complexity. It's not. The fix is so simple it's almost insulting. It's a hack, it's a kludge, and it is one of the most powerful ideas in all of reinforcement learning. Here's the solution. Are you ready for this? Be greedy most of the time, but every once in a while, do something completely, utterly random. That's it. That's the secret. Behave optimally based on what you know, but for a small fraction of the time, throw your logic out the window and just be an idiot. Pick something you know is worse, or something you know nothing about. This small dose of intentional chaos is the key. It's the escape hatch. It's the agent's way of asking, but what if I'm wrong? Let's make this real. Think about how you choose a restaurant for dinner. Most of the time, maybe 90% of the time, you exploit. You go to your favorite pizza place. You know it's a solid 8 out of 10. It's reliable. It's the greedy choice. But that other 10% of the time, you explore. You open Google Maps, close your eyes, and just jab your finger at the screen. You commit to going wherever it lands. Now that 10% of the time, you might end up at a terrible 2 out of 10 restaurant. You just wasted a meal. That was the cost of exploration. But you might, just might, land on a new 10 out of 10 spot. A new favorite. A place you never would have found if you just stuck to your greedy pizza-eating routine. You have now permanently upgraded your set of best options. That is the entire idea. The official nerdy name for this strategy is the Epsilon-Greedy method. That's Epsilon-Greedy. And as you see here, that little epsilon symbol is just a number representing our be an idiot percentage. It's usually a small value like 0.1, which just means 10% of the time. Here's the rule. It's a 2-line algorithm. Check it out. At every single step, before you pull a lever, you generate a random number between 0 and 1. If that number is bigger than your epsilon, so bigger than 0.1, you exploit. You act greedily. You choose the machine with the highest current Q value. This is what's going to happen 90% of the time. But, if that number is smaller than or equal to epsilon, you explore. You completely ignore your Q values and pick a machine, any machine, at total random. That's it. That is the entire fix. So why does this work? Let's go back to our trapped agent. Remember its beliefs? It thinks machine number 2 is the best with a score of 10, and machine number 3 is a dud with a score of 7. A 10% Epsilon-Greedy agent will act like this. 90% of the time it looks at its beliefs, sees that 10 is the max, and pulls the lever for machine number 2. But 10% of the time it hits the explore trigger. It closes its eyes and picks a machine at random. It might pick machine number 1, it might pick machine number 2 again. Or, it might pick machine number 3. Eventually that 10% chance will hit. The agent will be forced to try machine number 3 again. It'll get a new reward. Maybe this time it's 18. Suddenly its estimate for machine number 3, Q of 3, is going to go up. A lot. It might not be the highest yet, but the agent was forced to gather one more piece of data. And as it keeps playing, that 10% chance will hit again, and again, and again. Every single time it explores and lands on machine number 3, its estimate gets more and more accurate. The law of large numbers kicks in. That initial bad luck gets averaged out. Eventually, Q of 3 will climb past Q of 2. And the moment that happens, the agent's greedy choice flips. Now for the 90% of the time it's exploiting, it will be exploiting the correct true jackpot machine. It escaped the trap. This is the guarantee of Epsilon-Greedy. Because it never stops exploring, it ensures that over a long enough time, it will try every single action enough times to get a very, very accurate estimate of its true value. It solves the getting stuck problem completely. This all sounds great in theory, but what does this learning process actually look like, turn by turn? How does an agent's brain, its table of Q values actually update from 0 to genius. That's what we're doing next. Let's watch it learn. It's time to walk through the Epsilon-Greedy brain. All right, talk is cheap. You've heard the theory, you've heard the promise. Be stupid 10% of the time, and you'll get smarter. It sounds good. It sounds counterintuitive and clever. But I'm not going to just ask you to believe me. We are going to watch it happen. We're going to rip open this agent's skull and watch its brain rewire itself, turn by turn. Seeing is believing, and you're about to see the proof. But first, how does an agent actually learn from a new experience? When it gets a new reward, how does it update its belief, its Q value? It doesn't recalculate the average from scratch every single time. That's slow. That's inefficient. Instead, it uses a simple, elegant little engine to update its knowledge on the fly. And if you want to understand reinforcement learning, you need to understand this one formula. It's the incremental update rule. Take a look. This is the general form. Basically, your new belief is just your old belief, nudged a little bit in the direction of your error, how wrong you were. For our casino problem, it gets a little more specific. Check it out. Let's tear this apart. Because this isn't just math. This is the logic of learning in one single line. Look at the part in green. The reward you just got, minus your old estimate. This is the error. It's just asking, how surprised am I? How wrong was my last guess? Now look at the part in red. This is our step size. It's just 1 divided by n, the number of times we've pulled this specific lever. Notice something critical here. The more times we've tried an action, the bigger n gets, which means our step size gets smaller and smaller. This is beautiful. It means in the beginning, when our agent is clueless, it takes big learning steps. It's easily swayed by new information. But as it becomes more experienced, as n grows, it becomes more stubborn. Its beliefs stabilize. It becomes less swayed by one single lucky or unlucky pull. It learns fast, then settles down. That's the engine. Now let's watch it run. Here's our setup for the game. We've got a classic 3-armed bandit. And here's the hidden truth that the agent cannot see. The real average payouts are 2 for arm 1, 6 for arm 2, and 4 for arm 3. So arm 2 is the real jackpot. Arm 3 is decent, but it's a trap. Our agent is Epsilon-Greedy, with epsilon set to 0.1, so it's going to explore 10% of the time. And right now, its brain is a blank slate. All its counts and estimates are 0. Okay, let's follow along on this table. I'm going to narrate the agent's thought process for the first 7 pulls. Step 1. The agent knows nothing. All Qs are 0, so it's forced to explore. It picks an arm at random, and gets arm 3. The reward is 5. So its brain updates. The count for arm 3 is now 1, and its estimate for arm 3 is now 5. Easy enough. Step 2. Now it has a favorite. Its best guess is arm 3. So, 90% chance it's going to exploit. And it does. It pulls arm 3 again. This time the reward is 3. Calculating. So its estimate for arm 3 drops a bit, from 5 down to the new average, which is 4. Step 3. Its best guess is still arm 3. It exploits again, pulls arm 3, gets a reward of 4. Since its estimate was already 4, the new evidence just confirms its belief. The Q value for arm 3 stays at 4. At this point, a purely greedy agent would be completely stuck. But watch this. Step 4. The 10% be stupid rule kicks in. It's forced to explore. It picks randomly and lands on arm 1. It gets a pathetic reward of 1. It updates its brain. Q for arm 1 is now 1. It learns something useful. Arm 1 is probably a dud. Step 5. Back to business. The best option is still arm 3, so it exploits again, pulls arm 3, gets a 4. No change. Now for the aha moment. Step 6. The agent is happily pulling what it thinks is the best lever, but that 10% exploration trigger fires again. It closes its eyes, pulls a random lever, and jackpot. It pulls arm 2 for the very first time and gets a massive reward of 8. Its whole worldview just changed in an instant. Look at its brain after that pull. The Q values are now 1, 8, and 4. The best option is no longer arm 3. So what happens on step 7? The agent decides to exploit, but now its greedy choice, its argmax, is arm 2. It pulls the correct jackpot machine, gets a reward, and refines its new favorite belief. Did you see it? Let's just break down what happened. The agent started with a bad guess. After just a few pulls, it was convinced ARM3 was the best. A purely greedy agent would be stuck there right now, pulling that lever forever, trapped by a mediocre choice. But then, at step 4, it had its first escape. The 10% be stupid rule kicked in and forced it to explore. That's what saved it. And the magic moment was step 6. That random, exploratory pull on ARM2 completely changed its world. It discovered something that its greedy strategy would have never let it find. And that led to the New World Order. After that discovery, its belief about the best machine flipped. Its greedy choice was no longer the trap of ARM3. It was now the correct jackpot machine, ARM2. This is the process. This is learning. It started with a bad guess. It got stuck on a suboptimal choice. But its built-in, stupid randomness saved it. That 10% exploration wasn't stupid at all. It was the escape hatch that allowed it to break free from its own flawed beliefs and discover the truth. Epsilon-Greedy works. It's simple, it's robust, and over thousands of polls, this agent will zero in on the true values and spend almost all its time pulling the correct lever. But it's not perfect. Its exploration is, well, dumb. It picks completely at random. It doesn't care if it's exploring a machine it's tried 100 times or one it's never touched. It's inefficient. Can we be smarter about how we explore? Can we add some intelligence to our stupid choices? Yes. And that brings us to our first clever upgrade. A psychological trick you can play on the agent to make it explore all on its own. Next up, we'll look at hack number 1. The power of being overly optimistic. Okay, so Epsilon-Greedy works. It's our reliable workhorse. That 10% chaos factor saves our agent from getting trapped. But let's be honest, it's a little crude, a little dumb. That 10% exploration is completely random. The agent might explore an arm it has already tried 100 times, just because the random number told it to. It's exploration by brute force. It makes you ask the question, can we be more clever? Is there a way to encourage exploration that isn't just random? What if I told you that you could take a purely greedy agent, one with zero randomness, epsilon set to 0, and trick it into exploring all on its own? What if the secret to making an agent smart was to first make it completely, utterly delusional? Welcome to our first major hack, a beautifully simple psychological trick called optimistic initial values. Here's the idea. It's so simple you'll laugh. Instead of initializing your agent's brain with Q values of 0, representing ignorance, you initialize them to a wildly optimistic, impossibly high number. So look at the slide. Let's say you know the absolute maximum reward from any slot machine is 10. The hack is to do this. First, set all initial Q values to 20. You tell the agent that every single machine is a super jackpot, better than anything that's even possible. And second, you use a purely greedy agent. No epsilon, no randomness. The agent will always exploit what it believes is the best option. That's it. That's the entire hack. And it completely changes the game. It tricks the agent's own greed into doing the hard work of exploration for it. Let's watch this delusional agent play. So, here's our setup. We've got our same 3-armed bandit, where the true best machine is number 2. Our agent is purely greedy. And the hack? We've initialized its brain with delusional optimism. As you can see, Q of 1, Q of 2, and Q of 3 are all set to 20. The game begins. Pull 1. The agent looks at its Q values. They're all 20. It's a tie. So it has to pick one at random just to break the tie. Let's say it picks arm 1. It gets a real-world reward, let's say a 3. Now it updates its brain. The Q value for arm 1 gets updated from a delusional 20 down to a realistic 3. The agent's brain now looks like this. 3, 20, 20. Arm 1 was a disappointment. It didn't live up to the hype. So what happens on pull 2? The agent is purely greedy. It looks at its options. 3, 20, 20. What's the best choice now? It's definitely not arm 1 anymore. The agent's own greed forces it to try something else. It sees that ARM 2 and ARM 3 still hold the promise of that incredible 20-point reward. So it picks one. Let's say it picks ARM 2. It gets a reward of 8. It updates its brain, and Q for ARM 2 drops from 20 down to 8. The agent's brain now looks like this: 3, 8, 20. You see what's happening here? For pull 3, the agent looks at its options again. 3, 8, 20. What does its greed tell it to do? Try ARM 1, which it believes gives a 3, or ARM 2, which it believes gives an 8. No. It looks at ARM 3, the one arm it hasn't tried yet, the one arm that still holds the delusional, optimistic promise of a 20-point reward. Its greed forces it to choose ARM 3. This is beautiful. By setting the initial values high, we've weaponized the agent's own disappointment. Every time it tries an ARM, the reality of the reward brings its optimistic estimate crashing down to earth. This makes that ARM look terrible compared to the other ARMs it hasn't tried yet. So the agent's own greedy nature systematically drives it to try every single ARM at least once. It creates a powerful, built-in burst of exploration right at the start of learning. It's not random. It's a directed search, driven by a desire to not be disappointed. So check out this table comparing the two approaches. Epsilon-Greedy explores randomly, with a fixed probability, throughout the entire run. It's unintelligent exploration. But optimistic initial values is different. It explores by greedily choosing the ARMs that still have those high delusional values. This means it explores heavily at the start, and its exploration is much more directed. It prioritizes totally unknown ARMs first. This is a powerful trick. It's an elegant way to solve the initial exploration problem without resorting to pure randomness. But it does have a weakness. This initial burst of exploration eventually fades. Once the agent has tried all the ARMs a few times, its Q values will start to settle near their true values, and it will behave just like a normal greedy agent again. If the world changes, it might be slow to adapt. So while this hack gives us a more intelligent start, Epsilon-Greedy's persistent, random exploration might be better in the long run, or in a world that changes. This brings us to a new question. We've seen random exploration. We've seen disappointment-driven exploration. What if we could design an agent that is always smart about what it chooses to explore? What if, at every single step, it could ask, which of these ARMs is the most promising one to explore right now, based on both how good it might be and how uncertain I am about it? That level of thinking requires a more advanced tool, a method that formally balances potential with uncertainty. And that brings us to hack number 2, the pro gamer move, upper confidence bound. All right, so we've got 2 tools in our belt now. First, we have our reliable workhorse, Epsilon-Greedy, which explores by basically being stupid 10% of the time. And then we have our clever psychological trick, optimistic initial values, which tricks a greedy agent into exploring by making it delusional. Both work, but they both have a weakness. As we can see on the screen, Epsilon-Greedy's exploration is completely random. And that burst of exploration from optimism, it's temporary. It fades. They don't feel intelligent. They don't feel like a professional's tool. So, what if we could build an agent that was always smart about how it explores? What if our agent could explore with purpose? This is the sophisticated approach. This is the pro gamer move. This is for when you want to squeeze every last drop of performance out of your system. It's called upper confidence bound, or UCB for short. And the core idea is beautiful. Instead of just picking the ARM with the highest current value, UCB picks the ARM with the highest potential value. It asks a much smarter question. Which ARM, considering both what I know and what I don't know, has the best chance of being the ultimate jackpot machine? It balances greed with curiosity at every single step. And the way it does this is with a formula. Now I'm going to put it on the screen. It looks scary. It's designed to make you feel like you need a math degree. You don't. Stay with me. Check this out. Okay. Whoa. Don't click away. Don't let your eyes glaze over. This is what they do. They hide simple, beautiful ideas behind scary-looking symbols to keep you out. We're not having that. I promise you, this entire scary formula is just 2 simple ideas you already understand, smashed together. Let's tear it down. First, look at this part here, the QTiva. Look familiar? It should. This is our old friend. This is the agent's current best guess for the value of an ARM. This is the greedy part, the exploitation part, the how good do I think this arm is right now score. You already know this. We're halfway there. Now for the new part. This bit over here. This is the hack. This is the pro gamer move. Think of this as the uncertainty bonus, or the curiosity score. It's a bonus added to arms that we're not very sure about. Let's look at the two critical ingredients inside. First, you've got T, which is just the total number of pulls we've done so far. The ln of T part just means this bonus grows very, very slowly over time. This makes sure the agent never completely stops being curious. But NT of A, this is the magic. This is the number of times we've pulled this specific arm. And notice where it is. It's in the denominator. It's on the bottom of the fraction.
What does that mean? It means the more you've tried an arm, the bigger that n value gets, and the smaller the uncertainty bonus becomes. Think about it. An arm you've pulled 1,000 times? Its n value is huge, so its uncertainty bonus is basically 0. You're very confident. It's a known quantity. But what about an arm you've only pulled once? Its n value is tiny, so its uncertainty bonus is massive. The agent is basically screaming, "Wow, I barely know anything about this arm. It could be amazing. I should give it a huge bonus just in case." And that little C out front? That's just a tuning knob. You set it to control how much the agent values curiosity. A bigger C means a more exploratory agent. So let's see how this actually works. Imagine this scenario on the screen. Arm A has an estimated value of 8, and you've pulled it 100 times. Arm B has an estimated value of 7, but you've only pulled it twice. How do our different agents see this? A greedy agent sees 8 versus 7. It picks Arm A, no question. An Epsilon-Greedy agent sees 8 versus 7. 90% of the time, it's also picking Arm A. Maybe it gets lucky and lands on B with its 10% random chance. But the UCB agent, it sees something totally different. It calculates a score for each. For Arm A, the score is its value, 8, plus a tiny uncertainty bonus, because n is 100. But for Arm B, its score is 7 plus a huge uncertainty bonus, because its n is only 2. Suddenly, even though Arm B has a lower estimated value, its total UCB score, that's value plus uncertainty, is going to be higher. UCB intelligently, strategically, and deterministically chooses to explore Arm B. It doesn't need a random number generator. It uses math to find the most promising, underexplored option and goes right for it. This isn't random exploration. This is directed exploration. Now check out this table comparing the two. Epsilon-Greedy's exploration style is random. You could even say dumb. UCB is strategic. It's smart. Epsilon-Greedy asks, "Is it time to be random now?" UCB asks, "Which arm has the highest optimistic potential?" One needs a random number, the other is deterministic. And when it comes to performance, UCB often converges to the best arm much, much faster. UCB is more complex, yes, but it's often far more efficient. It's what you use when good enough isn't good enough. So, we've journeyed from a simple greedy agent that got trapped, to a clever hack that used randomness, to a psychological trick using optimism, all the way to this pro-level strategic UCB agent. We've cracked the casino problem. But let's be real. You're probably not going to be programming slot machine AIs for a living. So why does any of this matter? Why have we spent all this time on a simple casino game? Because this isn't about casinos. The slot machines are just a metaphor. This simple trade-off between exploring and exploiting, this balancing act between what you know and what you could know, it's not just the heart of reinforcement learning. It's a piece of logic that quietly runs the entire modern world. And in our final section, we're going to see the payoff. We're going to connect these simple casino algorithms to everything from the websites you use every day, to medical trials that save lives, and even to the full-blown AI that's changing the world. It's time to see why this casino math runs the world. All right, we did it. We beat the casino. We took a problem that traps most people in a loop of just good enough, and we solved it. But let's be real. You're not here to become a professional slot machine player. So why did we just spend all this time in a dusty digital casino? Why does any of this matter? It matters because this was never really about slot machines. The casino is just a metaphor for every single decision you have to make with incomplete information.
It's a pure, distilled version of the single most important trade-off in learning and decision-making, the exploration-exploitation dilemma. And you now have the toolkit to solve it. Just think about how far you've come. Look at this recap on the screen. First, you started with the obvious, logical, greedy strategy, and you watched it walk straight into a trap, getting stuck on the first good enough option it found. Then you learned the Epsilon-Greedy hack, that 10% stupid rule that used a little bit of chaos to guarantee you'd never get stuck again. Simple, robust, and it works. We got clever with optimistic initial values, a psychological trick to fool a greedy agent into exploring all on its own, just by making it a little delusional. And finally, you learned the pro-gamer move, upper confidence bound, or UCB, the sophisticated strategic method that intelligently balances potential and uncertainty to explore with surgical precision. You've gone from a naive agent to a strategic one. You've cracked the core problem. So, where does this show up in the real world? It turns out, this casino math isn't some obscure academic exercise. This logic, this constant battle between explore and exploit, it quietly runs the modern world. You interact with Bandit algorithms every single day. You just don't see them. They're the hidden engines optimizing the digital world all around you. Let's start with something you've probably heard of, A/B testing. The old way of doing this is pretty slow. You want to test a button color, so you show 50% of your users version A and 50% version B, wait 2 weeks, and then a data scientist declares a winner. The problem? For those 2 weeks, you were knowingly showing half your users the worse version. That's pure exploration, and it's super wasteful. But Bandit algorithms are the upgrade. When Netflix wants to test a new thumbnail for Stranger Things, they don't do a slow A/B test. They launch a Bandit. It shows a few people each version of the thumbnail. Those are the actions. As soon as one thumbnail starts getting more clicks, that's the reward. The UCB or Epsilon-Greedy logic kicks in. It starts exploiting the winning thumbnail, showing it to more and more people, while still occasionally exploring the others just in case it was a fluke. They are minimizing regret. They are making more money in real time by using the exact logic we just discussed. Now here's an application that's a lot more serious. Clinical trials that save lives. Imagine doctors are testing 3 new cancer treatments. The actions are the treatments themselves. The reward is a positive patient outcome. The old way? Assign patients randomly to each group and wait 5 years. Many patients in that trial will have received a treatment that doctors realized was inferior years earlier, but they had to stick to the protocol. The Bandit algorithm approach is different. It can ethically balance the needs of current patients and future patients. It exploits the treatment that is performing best so far, giving more patients the best chance at a good outcome, while still exploring the other treatments to gather the data needed to prove which one is truly superior in the long run. It's a way to learn faster and potentially save more lives by intelligently navigating that explore-exploit trade-off. And it's not just digital worlds or medicine. Think about robots that learn to grab things. When a robot arm tries to pick up a new object, every grip is an action. Does it work? That's the reward. A Bandit algorithm allows the robot to quickly explore many different ways to grip the object, and then exploit the ones that work best, without a human needing to program every single possibility. From ad placement to stock trading to dynamic pricing, this simple casino logic is everywhere. And now, the final step. All of these problems, every strategy we've discussed, they all have one giant limitation. In our casino, the jackpot machine was always the jackpot machine. The best action never changed. But what happens when the right choice depends on the situation? What happens when the best slot machine to play changes depending on what day of the week it is? This is the bridge from simple bandits to true, full-blown reinforcement learning. Think about a self-driving car. The best action, brake or accelerate, is not always the same. It depends entirely on the state of the world. Is the traffic light red or is it green? For a chess-playing AI, the best move depends entirely on the state of the board. What happens when the agent doesn't just need to learn the best action, but the best action for every possible context it might find itself in? That is the next level. That is where we leave the casino and enter the real world. That's where we get to the AI that truly learns, adapts, and makes decisions. And to see how that works, well, that's the topic for part 2. Make sure you're subscribed because that's where things get really interesting.